So we will continue watching first the pre-recorded videos from yesterday, okay, which actually we stopped at the photoelectric effects. Okay, so we will continue the next pre-recorded video, and then I will explain after that. Okay.
Assalamualaikum warahmatullahi wabarakatuh. Today we are going to cover chapter 27.5 and 27.6. These are the topics and the learning outcomes. For topic 27.5, photon scattering and Compton effect, the mass and momentum of a photon. Students should be able to define the momentum of a photon in relation with the quantum energy and describe briefly on Compton effect in terms of conservation of energy and momentum. And for the second topic, 27.6, the dual nature of light and matter, students should be able to state the de Broglie hypothesis and explain the dual nature of light and matter, and apply the Broglie wavelength of a particle formula. So we go to the first topic for today, the Compton effect. Compton assumed that if a photon behaves like a particle, its collision with other particles is similar to a collision between two billiard balls. So the X-ray photon carries both measurable energy and momentum, and these two quantities must be conserved in a collision. If the incident photon collides with an electron initially at rest, as in this figure, the photon transfers some of its energy and momentum to the electron. As a consequence, the energy and frequency of the scattered photon are lowered and its wavelength increases. Applying relativistic energy and momentum conservation to the collision described in figure, the shift in wavelength of the scattered photon can be described by this equation. Okay, if you can see here, the shift in wavelength delta lambda equals to the lambda minus with the initial lambda equals to h, or the Planck constant, divided by me, or the mass of the electron, times with c, the speed of light, okay, multiply with 1 minus cos theta. So the quantity h over me times c is called the Compton wavelength. Okay. This is h is the Planck constant divided by me times c is the Compton wavelength, and the Compton wavelength is given by this value 0.00243 nanometer. So the Compton wavelength is very small relative to the wavelength of a visible light, so the shift in wavelength will be difficult to detect if visible light were used. Okay, the Compton shift depends on the scattering angle and not the wavelength. So in this case, we can see that energy and momentum will conserve. Now we go to the second topic, the dual nature of light and matter. Light has a dual nature. It exhibits both wave and particle characteristic. The photoelectric effect that you have learned before and Compton scattering offer evidence for the particle nature of light. When light and matter interact, light behaves as if it were composed of particles. Interference and diffraction offer evidence of the wave nature of light. So for wave properties of particles, in 1924, Louis de Broglie postulated that because photons have wave and particle characteristics, perhaps all forms of matter have both properties. Furthermore, the frequency and wavelength of matter wave can be determined. So this is the de Broglie wavelength and frequency. The de Broglie wavelength of a particle is given by this equation. Lambda equals to h over p. H is the Planck constant, p is the momentum of a particle, equals to h over mv. M is the mass, v is the speed of that particle. Okay, and the frequency of the matter wave is also can be given by this equation. The frequency equals to the energy divided by the Planck constant. The dual nature of matter is quite apparent in these equations because each contains both particle concept. For particle concept, we can look at its momentum or mv and its energy. And for the wave concept, we can look at its wavelength and its frequency. So this is the example. We look at problem A, compare the de Broglie wavelength for an electron. This is the mass of an electron moving at a speed equal to 1 times 10 to the power of 7 meter per second with that of a baseball of mass 0.145 kilogram pitch at 45 meter per second. So we need to compare the de Broglie wavelength of the electron and the baseball. Okay, we insert the value for the electron, the mass of the electron and the speed into the equation, and we get the wavelength, the de Broglie wavelength, which is 7.28 times 10 to the power of negative 11 meter. And then we do the same thing for the baseball. Okay, we insert the value for the baseball into the equation, and then we get the wavelength, which is 1.02 times 10 to the power of negative 34 meters. Okay, if we compare here, okay, the baseball has much lower wavelength compared to the electron. Okay. This is the application of the Compton effect and the de Broglie wavelength. Okay, a practical device that relies on the wave characteristic of electrons is the electron microscope. Okay, this is the schematic of the electron microscope. A transmission electron microscope used for viewing flat and thin samples. Electron microscope has a great resolving power because it can accelerate electrons to very high kinetic energies, giving them very short wavelength. And typically, the wavelength of electrons in an electron microscope are smaller than the visible wavelength by a factor of about 10 to the power of negative 5. Okay, that's all for this topic. Thank you for watching. Assalamualaikum.
Okay, so let me share the slide first. Okay, so we'll continue first. Our topic from yesterday. Okay, so yesterday we learned about black body radiations. Okay, black body radiations. What is it all about? So I will try to explain back because this topic is very important when you learn uh, uh, the difference between classical physics and also modern physics. Okay, so when we talk about classical and modern physics, so regardless of the topics, we should know about the different between uh, classical and modern physics. Okay, so in the world of quantum, okay, how can we define or how can we relate our world in the quantum base? So is it because of the attempts to explain the behavior of matter at the atomic level? Okay, we'll find that the classical physics is were unsuccessful. Okay, were unsuccessful, failure. Okay, so we cannot use a classical physics, a normal classical physics, when we try to explain a behavior of matter on the atomic level. So it's very it is not a good approach when you use a classical physics because it will give you a failures. Okay, but when we talk about behavior of matter at the atomic level. That's why, okay, the physicists around the 1930s, okay, introduced quantum mechanics. Okay, a versions of mechanics called quantum mechanics was highly successful when explaining the behavior of atom, molecules, and nuclei. Okay, atom, molecules, and nuclei, which means if you try to bring out, you will try to see how can this happen. So you can look at a simple graph of intensity versus frequency here. Okay, so when you look at the intensity versus frequency, as the frequency increase, okay, the intensity, as the mention of the classical prediction, in the classical prediction will predict that as the frequency increase, the intensity will keep going up, will keep increase the value. But using the experimental, okay, by the Plancks, okay, Maxwell Plancks, the physicist, okay, did the experimental and observed that, okay, it is not like that. Okay, the intensity should be at increase at one point and reach the maximum peak, okay, maximum value, the optimal value, and then it will decline. Okay, will decline, and this is what happened, and this curve is explained by the quantum. Okay, so that's the difference between quantum and also classical predictions, right? So the black body radiations and the Planck's hypothesis. Okay, so when you look at the subtopic of this is a black body radiation. When we talk about black body, it's not just the body with no colors. Okay, because we understood that, okay, when we have when we see things in color, that is because of the light that go through our eyes. Okay, okay, of course it's being processed by our brain, but that is due to the frequency. Okay, due to the frequency, and of course the frequency, where we have v equals to f lambda. Okay, remember frequency also v over lambda. This is a wavelength and this is the frequency. Okay, so frequency and wavelength is actually inversely proportional to each other. So when we try to plot the intensity, okay, the intensity against the wavelength lambda, right? So we can see that, okay, at the different temperature, okay, look at the curve. Every curve is have different temperature. Okay, for example, this is the 5,000 Kelvin. Okay, and in the air we have 2,000 Kelvin. And of course, you look at the peak of those temperature. Okay, when we see at 5,000 Kelvin, Okay, the peak or the optimum value for the curve graph is at the visible range. Okay, and for 4000 Kelvin is at the in the regions of mix of the visible and infrared region here. And you look at the 3000 is already in the infrared region, and 2000 Kelvin of course is that it has a 2000 in the region of infrared. So we can see that different temperature will give you different peak of the intensity. Okay, so that is number one. And we can say that as a wavelength increase, okay, as a wavelength increase, okay, the peak of the intensity have been shifted to the right, shifted, okay, shifted to right. Okay, dia berpindah ke sebelah kanan, shifted to the right, and from the visible range to the range of infrareds. Okay, so what is this all about? Okay, so we look at the explanation. The spectrum of radiation depends on the temperature and the properties of the object. Okay, so the main point here, we need to know the temperature of the object, the properties of the object in order for us to understand the spectrum of radiations. Okay, because an object at any temperature will emit a EM radiation, electromagnetic radiations, called thermal radiations. Okay, this is what we call thermal radiations. So a careful study of thermal radiation shows that it consists of continuous distributions of wavelength from UV here at this point, from UV, okay, visible range, and lastly the infrared. So we can see that the different, okay, a low temperature, okay, we can see that at low temperature, the wavelength of thermal radiation are mainly in the infrared region. So that's what we call uh, uh, the wavelength of the thermal radiation have been shifted to the right. Okay. So when we talk about black body, so now we want to explain about the black body. So an ideal black body, a very good black body means that, okay, that particular object must be what? Absorbs all the light that is incident upon it. Okay, meaning that when you have a body, you have an object, and everything. Okay, remember when you have object, okay, you have maybe there are a certain ways, okay, to deal with object. Okay, so when you put maybe you give light, okay, lights and incident on the object. So this is, let's say, the object. So maybe the light will be reflected. Okay, reflected, and maybe the light will be transmitted. Okay, transmitted means it can go through the objects, and maybe it will absorb. Okay, absorb. So there are three possibilities when light encounters an object. Okay, maybe it can reflect it, maybe it can transmit it, and lastly it can be absorbed. So for the ideal black body, all incident light, okay, has been absorbed into the matter. So that is the ideal black body. And black body is a theoretical object. So it's a theoretical, it's not just a things with the black color, okay, but it means that the black body is a theoretical, okay, theoretical object that absorbs 100% of the radiation that hits it. Okay, therefore it reflects no radiations and appears to be perfectly black. Okay, so I'm around here. Okay, an ideal black body is also an ideal radiator if we measure the intensity of the electromagnetic radiation emitted by an ideal black body. We will find that. Okay, so look at the intensity versus frequency here. Okay, intensity versus frequency. So at the 6000 Kelvin, and the difference between 6000 and 3000, 6000 and 3000. Now the intensity is against the frequency. Look, this is frequency, remember. frequency is equivalent to V over lambda. Okay, before this, okay, we are plotting intensity against lambda. So we can see that the graph has been shifted to the right. And now you can see that as the temperature at the low temperature, it's been shifted to the left. Okay, that is due to the what we plot against the intensity against frequency and not against wavelength. Okay, right? So you can see here the difference between 6,000 and the 12,000 Kelvin. Okay, so when the temperature increase, so the peak of the displacement have been shifted. Okay, and now let's say at 6,000, okay, the peak is at the regions of maybe infrared, or maybe yeah, this one is considered to be infrared or UV, okay, and not the visible range. And when the temperature increase, okay, when the temperature increase from 6,000 to 12,000, you can see that the peak is at the visible range region. Remember, visible range region is from the 4,400 to 700 nanometers. This one is the wavelength. Okay, if you want to calculate the lambda, you should use the formula of F equals to V over. You want to calculate the frequency, you should use the V over lambda. So the distributions of energy in the blackbody radiation is independent of the material from which the body is constructed. Okay, independent, meaning that it have no change. It can harm anything. The blackbody radiation is independent. Okay, it cannot depends on the material. Okay, because it only depending on the temperature by this equation. The peak frequency is given by, so this is what we call it, peak frequency. Okay, so remember when we have a plot of graph, so the peak frequency have been shifted to the right. Okay, if we plot intensity against lambda wavelength, so we can actually calculate the peak frequency, which given by this constant value times with the temperature. Okay, constant value against temperature, and we will get the frequency, which is in hertz or second negative 1. Okay, the peak wavelength increases linearly with the temperature. Okay, meaning that when the temperature increase, so the peak wavelength also increase because it increase linearly. This means that the temperature of a black body can be determined by its color. Okay, so obviously, okay, the wavelength, as a certain wavelength, there will be a different color. Due to what? Due to the temperature of the black body. So the color is determined by the temperature, or the temperature of the black body can be determined by its color. When you look at the things that glow, okay, differently from yellow, from green, from blue, okay, in physics we actually, okay, it depends on the temperature. Okay, the temperature and the color itself will give a different value of temperature. Okay, this is what we call as the ultraviolet catastrophe. Sometimes they will ask you what is an ultraviolet catastrophe. So you need to draw this kind of graph, okay, to explain about the classical prediction and also the experimental observation. Look at this is intensity versus frequency. Okay, so the classical prediction is called the ultraviolet catastrophe. Remember the word ultraviolet catastrophe. Okay, maybe they can ask you inside the MCQ questions. Okay. Okay, so for example, we have a wood fire at 1,500 Kelvin, puts out a peak radiation at about 2,000 nanometers. Okay, 2,000 nanometers around here. Okay, around here. This is in the micrometer, so in nano it should be 2,000 nanometers. 98% of its radiation is at a wavelength longer than 1,000 nanometers. So around here, this is 1,000 nanometers. Okay, and only a tiny portion at a visible wavelength. Okay, look at this side. There are tiny portion for at 1,500 because 1,500 considered to be somewhere around here. Okay, because it should be lower than 2000 Kelvin, and you can understand that. Okay, there will be a 98% of its radiations is on the wavelength of the infrared. Okay, so what does it mean? Okay, a campfire, okay, a wood fire, okay, of course from the campfire can keep one warm. Okay, boleh bagi panas, but it is a poor source of visible light. Okay, source of visible light, meaning that, okay, from the campfire alone, okay, we can feel the warmth, okay, but it cannot glow, okay, in the and to be in the source of as a source of a visible light. That's why, okay, we cannot see things in the dark. All right, when we have a campfire, it's just a glow at that particular point because it has only a tiny portions of the visible range. Okay, all right, so the effective temperature of the sun, let's say sun is around 5,700 Kelvin. So slightly compared to this one, maybe it's around this one, but okay, slightly uh, higher than the 5,000 Kelvin. Using the Wien's law, one find a peak emission per nanometer wavelength at about 500 nanometers, okay, in the green portion of the spectrum near the peak sensitivity of the human eye. Okay, so you can see that maybe around 40% of the peak is actually at the visible range, which with compared to 1,500. So sun, the temperature of the sun, look at temperature of the sun is around 5,000 Kelvin. Okay, around 5,000 Kelvin. Of course, it's not uh, really matter, but we know that it's above 5,000 Kelvin. So obviously, at the 5,000 Kelvin, look at the curve. The curve have a maybe 20 or 30% of the radiations is in the visible range. So we can see when the temperature at the more than 5,000, we can see these radiations. Okay, we can look at this range. That's why at the visible range, we can see at the 5,000, we can see a lot of colors. We can see colors. Okay, at this point, the colors is at the green portions of the spectrum. Okay. So the Planck discovered that he could reproduce the experimental curve by assuming the radiation in the black body came in quantized energy packets. So look at the intensity versus frequency. So this is the ultraviolet catastrophe, and we have a Planck's like this. So this one is explained. Okay, Planck, Maxwell Planck discovered this. He could reproduce the experimental curve. Okay, how can he produce the experimental curve? By assume, the physics use the word assume that the radiation in a black body, okay, radiation black body came in quantized energy packets. Okay, came in quantized energy packets. Look at the word energy packets, meaning that, okay, when you talk about energy, okay, quantized energy packets mean that energy is comes, let's say this is light travel, so it comes in a very, okay, in numerical numbers of energy, numerical numbers. So we can count how many energies. Let's say this is considered to be 1, 2, 3, and so on. Okay, because the energy, when it comes in quantized, meaning that we can calculate the energy, we can give the number to the energy, okay, and it can calculate. All right, so that's why we are saying that the energy, okay, is given by E equals to HF using the Planck's constant. Of course, he wants to put his name in the constant value, so the Planck's constant times with the frequency. And of course, when you put the n, meaning that we should find the number of energy, so you put another n at in the beginning of the HF. And now you know that the n is 0 until infinity. So we can calculate the energy in terms of in terms of the quantized energy packet is in order to reproduce the experimental curve. Remember, the experimental is in the quantum quantum. Okay, and this one is the classical. And the Planck's constant is 6.63 times 10 power of negative 34. Look at the constant value, joule second. Okay, the unit for Planck's constant is joule second. So when you talk about energy, so you need to define. Okay, normally at the quantum level, the energy is given in the unit of electron volt. So you need to know how can we measure electron volt, because one electron volt is considered to be what? 1.6 times 10 power of negative 19 joule. Okay, so that is the value of one electron volts. Okay, 1.6 times. So we need to know the conversions of one electron volt to 1.6 and to the joules. Okay, look at the questions here. All right. Okay. Look. So how can they measure, or how can they convert from one electron volt to the joule? Because they want to cancel out the electron volt and then replace it with the joule, because the Plancks, yeah, have joule inside the question. Okay, inside the constant, so we need to cancel out joule and in order to get something else. Okay, so this is the good example. All right, so now you look at the photoelectric effects. Okay, so the photoelectric effects is introduced to you by Einstein. Okay, Albert Einstein. Okay, he suggested that the light comes in bundle of energy. So he actually took the Planck's hypothesis of energy quantization and suggested that, okay, maybe he did some calculations there, okay, to explore or to introduce to you the photoelectric effects. Okay, what is the photoelectric effect? Look at the word photoelectric effect. Photo and electric. Photo means light, cahaya. Okay, and electric means electric and the effect. So what is photoelectric effect? And from this experiment or from these introductions to the science community alone, okay, he have won the Nobel Prize, the physics Nobel Prize. Okay, so the Einstein suggested that the light that comes in bundle of energy and called photons. For those who can know, this is not proton, it's a photon. Okay, photon. Okay, this is not a proton. Proton means a positive charge, and this one is a photon, meaning that a light comes in the bundle of energy. Okay, so Einstein took some hypothesis or how can we define energy quantization before this, when the energy comes when we can calculate the energy, sorry, can calculate light in terms of energy packets. Before this, E equals to NHF. So Einstein took this theory and tried to introduce the photoelectric effect. Okay, from this theory, it actually comes from the Planck's hypothesis of energy quantization. But okay, in the photon alone, the energy of a photon of the frequency, okay, Einstein suggested that E is equivalent to HF. Okay, E equivalent to HF. Again, he took the Planck's constant and with the frequency to get the E energy. And the unit for energy here is the joule. Ingat, joule. Okay, so definitely we always calculate in joule because joule is the SI unit for energy. Okay, but in the questions, maybe they will give you electron volt. So you need to do some conversions. Okay, thus the energy in a beam of light of frequency F can have only the value of HF, 2HF, meaning that this is N equals to 2, this is N equals to 1 over here, and this one is 3HF, and so on. Okay, so meaning that you cannot have energy at 1.5 HF, for example, 2.5 HF. Okay, it must be in exact amount of 0, 1, 2, 3, and so on. So that's why the energy of photon of frequency cannot be in the decimal point. Okay, meaning that not the energy, but the number of photon of the frequency, because it comes from the energy quantization. Remember what is quantization here? When we talk about energy quantization, remember HF. E equals to HF. All right. So in the Einstein model for photon model, a beam of light can be thought as a beam of particle, each carrying the energy hf. Okay, remember when we talk about light, okay, before this we always know that light is made from wave. Okay, it's a wave. So remember when we talk about wave, so light is a sinusoidal. Okay, because it is a wave where we have a crest or throw, so light is a wave. But okay, when the modern physics come, the quantum come and try to explain the classical part, successfully can explain the classical part, and then the Planck and Einstein come with the energy quantizations of light. Okay, light energy quantization when they actually try to imagine or try to assume that and the light must come as a particle, uh, like the one that Maxwell thinks before this. Light will come as a particle, not as a wave. Okay, so each light will carry a energy, HF, 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 HF. Okay, if the beam of the light is made from an intense while keeping the frequency the same, the result is that the photon in the beam are more tightly packed, so that more photon pass a given point in a given time. In this way, more photons, it is more, okay, more photons. Okay, consider that F is the same, F the same. Okay, this is a less photon. Okay, so in this way, more photons shine on a given surface in a given time. So when you can, okay, if you can catch the photon, so this is like a 2 photon, and it's like a 5 photon. So 5 is bigger than 2, so we can say that the 5 photons have high intensity light beam when compared to 2 photons. Okay, so what is the photoelectric effects? Okay, the photoelectric effect occurs when a beam of light strikes a metal. Okay, remember the photoelectric effects. Okay, remember that the light comes with a bundle of energy packets like this one. Okay, this is HF, this is HF, and this is HF, and try to hit this metal. So this is a metal. Okay, remember that is a metal, and remember when you look at the metal, okay, metal is made from atoms, okay, and atoms, the arrangements of the atom in the metal, because we know metal is a solid, is very close, okay. But when we talk about metal alone, okay, atom, okay, you know that the proton is on the inside, where the electron is on the outside, huh? Orbiting at each atom. So you can see that the electron is in the valence, and that's at the outside. Okay, and then what happened is when the light, okay, when the light striking the metal, okay, it will strike, the light will strike this electron. The light will strike this electron, strike this electron, strike this electron. And what happened is it will break the change of this electron, and the electron now have been released from the atom. How can you know that the atom is released? Yes, they must have a conditions. What? Okay, each metal will have a minimum amount of energy. Assuming that each metal will have a minimum amount of energy, okay, and that what we call as the work function. Okay, this each metal will have its own work function. Okay, so what is the equations of the work function? Equation of the work function is H F naught, and F naught is what we call as cut of frequency, meaning that the frequency that the electron will release. Okay, so if you want to cut the electron, you must have a cut-off frequency. What is the cut-off frequency? Then you need to measure. You need to know what is the work function here. Okay, so try to imagine when light comes at a bundle of packets of energy, and then it will strike the metal, striking the metal which strike the electron to release the electron. And then when the electron release, it will be accelerated. Okay, electron, it will be accelerated to the collector here. Okay, when electron release, it will be accelerated at a very high speed. Accelerated, okay, dipecutkan, decelerated to the collector in order to complete the circuit. And then from that we know, from the emitter alone, okay, we can see that the emitter have been deflected to the certain value, meaning that we can have current. So that's how the photoelectric effect. So remember, photoelectric means from light, okay, you can create the electric. From light, okay, not just a normal light, but light comes with the packets of energy. Okay, what is the packets of energy? HF. So light comes with a certain energy. So this is the energy of light. Okay, let's say the energy of light is 10 electron volts. And the work function is also, everything here is an energy. Okay, regardless of the terms used. Kmax. Kmax is the kinetic energy. Okay, kinetic energy maximum, and W naught is the energy, but we call that as a work function. Okay, look at here, W naught is the energy required to eject an electron, so that is what we call WO. WO is the work function. It is not a work, but the term is used with work function. It is a energy. So don't get me wrong. Don't or confuse with the term, because although the name is work function, it is an energy. Okay, it is an energy, and the value should be electron volt, because in very high speed. So if the work function, okay, let's say E is 10 electron volt, okay, work function is 10 electron volt. So how can we get the electron to be released from the atoms? Yes. Okay, so it's either to be equal or greater than. Then we can have a Kmax. Okay, and the Kmax is the when you accelerated the electron, so that is the value of Kmax. So we can measure the value of Kmax by deducting the electron, the energy to the work function. So if you have E equals to 20 electron volts, for example, I give just a random value. So work function is 10 electron volt. So K max is definitely 20 minus 10, you get 10 electron volt. So that will be the value. So, okay, so that is what we call as a photoelectric effects. So this is the classical predictions in the photoelectric effects, that any beam of light of any color can eject electrons. Okay, so that is the number one classical prediction. And number two, the maximum kinetic energy of an ejected electron should increase as the intensity increase. Okay, but this is wrong. Why this is wrong? Because look at this observation. Light must have a certain minimum frequency, because energy is made from HF. This is Planck constant. The value will be constant, and the energy of light will be depending on the frequency. It cannot be any color. Any color means any frequency. Okay, so this is not a correct word, because the light must have a certain minimum frequency. If it does not, let's say the E is 10 electron volt and your W naught is 20 electron volt, then the photoelectric effect cannot happen. Okay, you cannot make the photoelectric effect. You cannot get the Kmax. Okay, and then observation number two, more intensity results is more in more electrons of the same energy. More intensity resulting in the more electrons of the same energy. So we are talking about, okay, the quantity of electrons have intensity will results in more electrons of the same energy. How can we make same energy? Because it comes with the same frequency. Okay, and of course the classical prediction cannot explain what the quantum will explain below. Okay, so each photon's energy is determined by its frequency. Okay, if it's less than the work function, the electron will not be ejected no matter how intense the beam. Okay, remember, if it less than the work function, the electron will not be ejected, no matter how intense the beam. An electron is ejected only if an incoming photon has energy at least equal to the work function. At least equal to the work function. An electron will be ejected. Remember, okay, so the value of the cut-off frequency, the incoming, the F should be equal to F naught ejected. Okay, or F should be greater than F naught. So the character is F is like this. So this is the incoming photon. This is the method, the cut-off frequency. So you can calculate the cut-off frequency by dividing the work function to the Planck's constant, and then you will get frequency. Okay, so a beam of white light containing frequencies, okay, from 4 times 10 power of 14, 7.9, 10 power of 40 is incident on the sodium surface, which has a work function. Okay, look at here. This is the work function. Look at the word work function. So this is WO, 2.28 electron. What is the range of the frequency in this beam of light for which electrons are ejected from the sodium surface? So how can make the electrons ejected? So we need to know the range of the frequency. Given here, 4 times 10 to power of negative, 4 times 10 power of 14 until 7.9. So from here, we need to calculate the cut-off frequency. So that's why we are saying to calculate the cut-off frequency. Remember, and the work function is given in the electron volts. Again, I will explain 2.28 in the electron volt because we want to cancel out with the Planck's constant, which have joule seconds unit. So joule and joule. So you cannot 2.28 divided by 6.63. You will not get the right answers. So you need to convert it to the joule. So 1 electron volt is equivalent to 1.6 times 10 power of negative 13 and 19 joules. So joule, electron volt and electron volt, you cancel out. Joule and joule, you cancel out. So in the end, 2.28 times 1.6 times 10 power of negative 19 divide with the 6.63 times 10 power of negative 34, and you will get 5.5 times 10 power of 14 hertz. Okay, so meaning that, okay, this is the cut-off frequency, and we have 4 until 7.9. So it should be at 5.5 until 7.9 times 10 power of 14 hertz in order to get the electrons ejected. So that is the answers. And the second one, find the maximum kinetic energy of the photoelectrons. Okay, this is another terms of photoelectric. So the kinetic energy. So meaning that we should find the K max. What is the K max? Okay, here. Okay, they didn't put E because you already know E equals to HF. Okay, HF minus HF naught. Okay, or 2.28. Okay, again, we need to cancel out electron volt and electron volts, and in the end, you will only left. So remember, the frequency is second negative 1 over second. So second and second, it will be cancelled out, and in the end, the last term, uh, term left will be joule. So that's why the answer is in joule. 1.59 times 10 power of negative 19 joule. Okay, so that is the first part, right? And this is the the applications. Okay, so this is the topics from today, which is the chapter 27.5. Okay, which is photon scattering and the Compton effects and the mass and the momentum of a photon. Okay, remember mass and momentum of a photon, and lastly the dual nature of light matter. Okay, so this is the Compton effects. Okay, when they have um, when electron, okay, in the process of striking an electron, okay, striking an electron, so the incoming, okay, remember this is okay, okay, which means it comes with the E equals to hf, and try to hit the electron. So what happened is, when striking the electron at, okay, there are some collisions happens when you're striking the light and the electron, and the light will go to this part. Okay, it comes to the FO, okay, which means the original frequency, and the lambda naught, and okay, it's scattered to the frequency prime and also lambda prime, and the electron will scatter to the phi at a certain phi and with a certain angle. So the scattered photon, okay, having lost an energy, has a longer wavelength and a lower frequency than the incident photon. Okay, so this should be the incident, and this should be the scattered photon. Okay, the scattered photon having lost an energy because what? Because some of the energy, okay, have been transferred to the collisions between the incident photon and also the electron. And of course, the electron recoils just as if struck by a classical particle. Okay, in the Compton shift, okay, shift in the wavelength, we consider the delta lambda, which is the lambda minus lambda naught, over a Planck's constant over me, mass of the electron here, and times with the speed of light, okay, times with 1 minus cos theta. Okay, this is the original Compton shift formula. Okay, and the quantity is of h over mec is called Compton wavelength. It's not quantum, it's a Compton wavelength, because the Compton, okay, the physicist Compton have discovered what happened during the collisions between the incident photon and also the electron. So now we want to see the effects of the Compton effects. Okay, so the Compton wavelength, okay, meaning this is the Compton wavelength alone. It is equal considered to be, okay, 0.00243 nanometers. Okay, it's already calculated here. Okay, very small compared to the visible light, right? And the Compton shift depends on the scattering angle and not on the wavelength. It's only depending on the scattering angle and not on the wavelength. Energy and momentum were conserved. Okay, again, how to get the lambda, the delta lambda or lambda minus lambda naught? Okay, remember lambda minus lambda naught. This is lambda. This is lambda naught. Here, it's based on the Compton formula. Okay, light has a dual nature. It exhibits both wave and particle characteristics. Okay, so as quantum physics advance to the uh, as the time advanced, the quantum physics also discovered that actually light has a dual nature. Okay, has a dual nature. So that is what we learn in our secondary school. Okay, because it should exhibit as a both wave and particle. So wave and also particle, two different things, wave and also particle characteristics. Okay, the photoelectric effects and the Compton scattering offer evidence for the particle nature of light. When light and matter interact, light behave as it were composed of a particle. When light and matter interact, okay, light tadi, okay, cahaya and matter, okay, interference and diffraction offer evidence of the wave nature of light. Okay, remember, okay, before this we already learned about interference and diffraction. That is how can we explain when light in terms of wave? We cannot explain interference and diffraction when light is in the particle. Okay, so photoelectric effect, Compton scattering, yes, is a particle characteristics. But for the interference and diffraction in the previous chapter, okay, offers evidence for the wave natures. Okay, so in 1922, Louis de Broglie postulates that because photons have wave, photon have wave and particle characteristics, perhaps all forms of matter have both properties. Furthermore, the frequency and the wavelength of matter wave can be determined. Okay, the broad wavelength and the frequency is given by here. Okay, lambda is equivalent to the Planck's constant over p. What is p? A momentum. Okay, what is momentum? H over mv. All right, and the frequency is given by the matter by the use of like a cut-off frequency using the energy against the Planck's constant, or E equals to hf. F is equals to E over h. The dual nature of matter is quite apparent in this equation because each contains both particle concept. Okay, which means we have mv and we have E. Okay, both particle concepts. Okay, dua-dua pun menggunakan particle and wave concept. So wave concept apa? Lambda and also frequency. Okay, so that's why De Broglie wavelength and frequency. So De Broglie actually took this opportunity to combine, or not to combine, to differentiate between light acting as a wave and light acting as a particles, but in his term, which means the Broglie wavelength and the Broglie frequency. Okay, so when we combine, it becomes like this. Okay, what happens to the wavelength? Wavelength will have h over mv. Okay, and frequency is equivalent to E over h. Both of them have Planck's constant. Okay, this one is an energy. Okay, this one is a term. Frequency is the term, but for wave concept, and energy here is for particle. While this one, okay, the mv or p, okay, is actually for the particles, but for lambda is for wave. So it combines nicely in order to explain that light have a duality behavior. Okay, so look at the examples, right? Compare the Broglie wavelength for an electron moving at a speed equal to the 1 times 10 power of 7 meter per second with that a baseball of mass 0.154145 kilogram pitch at 45 meter per second. Compare this wavelength and then of an electron. Okay, so the solution is right. Compare the de Broglie wavelength of an electron and the baseball. Okay, so we need to compare between the wave, the Broglie and also the de Broglie wavelength, and also the baseball wavelength. Okay, so use the Planck's constant, right? And ME is the mass of the electron, and this one is the velocity of the electron. While for the baseball, we have a Planck's constant, okay, the mass of the baseball, and also the speed of the baseball. And you can see that from here, you can have the wavelength. Okay, the wavelength 7.28 times 10 power of negative 11 meters. And for the wavelength of the baseball is 1.02 10 power of negative 4 meters. Okay, it's very, very small value of wavelength. So this is the application, the electron microscope. Okay, so you should know how what is the electron microscope. Before this, we all just heard about the electron microscope. So it's actually used the concepts of electron, the characteristics of electron. So the electron microscope has a great resolving power because it can accelerate electrons to very high kinetic energies, given them very short wavelength. Okay, if the kinetic energy very high, then the wavelength will be shorter. Okay, and typically the wavelength of electron and electron molecules are smaller than the visible wavelength by a factor of 10 power of negative 5. Okay, so I think we'll take a break for 2 minutes before we continue. Okay, so let's continue by watching the pre-recorded video. Okay, before we continue, right?
Welcome and good morning, everyone. Today, I would like to present the new chapter about atomic physics, which is in the chapter 28 from your textbooks. So next, we go through to the 5 main subtopics that are listed from our lesson plan. But from my video, I just focus only 2 sections that is similar from our textbooks, which the first section 28.1 to discuss about early models of the atoms, and also section 28.2 to discuss or to study about the spectrum of atomic hydrogens. The rest 3 subtopics will be continued to the next video. According to these 2 subtopics, so there are 5 learning outcomes needs to be achieved by the student at the end of this chapter. The first one, students should able to describe the first early model, which known as the Thomson's model. Number 2, the second model of atoms. Students should able to describe also what is the Rutherford's model of the atoms. Number 3, students should able to describe emission and absorption spectra. Learning outcome number 4, students should able to state the line series of hydrogen spectra. And the last one, number 5, students should able to calculate the wavelength in Balmer series, and also there are another 2 series which called as Lyman and also the Paschen series of the spectral line. So what is the Thomson's model? So basically the Thomson's model was discovered by the scientist named J.J. Thomson. So he suggested that this model of the atom as a volume of the positive charge with electron embedded throughout the volume, which looks like much looks like the seeds in the watermelons. So as you can see from this figure, so this is the Thomson's models looks like. So there are 2 particles, which includes the electron and also the proton or positive charge. So as you can see, the blue one is the electrons, which are much small negative charge located at the various location within the atoms, and surrounding these electrons are the positive charge or the protons of the atoms that are distributed continuously in the spherical volume. So the second models of atom was modified by the scientist named Ernest Rutherford in the 1911. So he performed one critical experiment showing that the previous model, known as the Thomson's model, couldn't be correct. So what he did from his experiment, so he used the alpha particles or helium atoms as a beam of light as showing in this given diagram. So this light of alpha particles was projected against a thin metal foil here. Okay, so as the results, okay, so from this experiment, so most of the alpha particle will pass through the foil as if it were empty space, but a few particles were scattered, okay, were scattered like this at the through a large angle, okay, through the large angle, and some even of the light will traveling backward, okay, as the target here. So such large deflection were not expected. But in the previous model, in the Thomson model, a positively charged alpha particle would never come close enough to a large positive charge to cause any large angle of deflection. So based on his experiment, so Rutherford explained that this result by making the assumption the positive charge in the atom, which is at the center here, was concentrated in the region called the nucleus that was small relative to the size of the atoms. And then he also visualized the atoms of electrons are orbiting the nucleus much as the planets orbit the sun. But there are two basic difficulties of this planetary model in the way to explain it as a model of the atoms. Number one, the first difficulties was an atom emits certain discrete characteristic frequency of electromagnetic radiation. And then the second difficulties was the electron will undergo a centripetal acceleration. So as the electron radiates the energy, so the radius of its orbit steadily decreases and it will increase the frequency of revolution. So as the result, this will lead the increasing frequency of emitted radiation and will have a collapse of the atoms as the electron spirals into the nucleus. Atomic spectra can be classified into two types. The first one is emission spectra and the second one is absorption spectra. So this figure shows example of emission spectrum. So as you can see from this, okay, hydrogen atoms, mercury atoms, and also the neon gas atom. So different atoms will have a different value of wavelength, which is from this figure, it is in the unit nanometer. So how the emission spectrum can be worked? So it is performed when the emitted light is analyzed using the spectrometer. So as the results, we can see the discrete bright lines. So each bright line's color will give the different value of wavelength. Okay, so for example, in the hydrogen atom, we have the red color value. So the value of red color here will give the value of wavelength, okay, in the range between 600 to 700 nanometer. Beside that, we also have hydrogen also can be seen the blue color of wavelength, the purple color of the wavelength, and also the green color of wavelength at the certain value of wavelength. So different color will give the different value of the wavelength belongs to that atom. So as conclusion, we can say that the wavelength of each spectrum are characteristics of the element emitting the light. Every single atom is capable of emitting electromagnetic radiation. The discrete line spectrum of an atom basically describes all the wavelength of light that is emitted by that particular atoms. And hydrogen atom produces a discrete line spectrum in the visible light region that seems to follow some types of the pattern as shown in, you can see from this figure. So this is the visible light spectrum that given by the different colors of wavelength, which tell us that the hydrogen atoms emits 4 types of the light in the Balmer series that each will correspond to the following wavelength quantity. Okay, so starting from the lowest wavelength is which is at 410.2 nanometer until the largest wavelength here, which is stated at 656.3 nanometer. In 1885, J.G. Balmer was able to show that the visible light of hydrogen spectrum will have the wavelength that follow the Rydberg equation, as showing in this equation. So in the way to calculate the wavelength of each spectral line, so you may use this equation. So the equation is given by 1 over lambda. So the lambda here is referred to the wavelength of the light that is emitting by the hydrogen atom equals to R constant multiplied by 1 over 2 square minus 1 over n square. So the given R H here is referred to the Rydberg constant value and has the fixed value, which is the value is equals to 1.097 times 10 power of 7 in the unit per meter. And the n here is referred to the principal quantum number, which is it is the positive integer number, and it start this number by 3, 4, 5 until infinity. So in general, the Rydberg equation is given by this following equation. To calculate the wavelength, okay, so the given formula here, okay, as you can see here, 1 over wavelength lambda. So the lambda, basically, this is in the unit meter, equals to RH constant multiplied by 1 over m square minus 1 over n square. And remember, the R constant or the Rydberg constant, this is given by 1.097 times 10 to the power of 7 in the unit per meter. And the value for m and n is referred to the positive integer of principal quantum number. So the integer of m should be less than n number. So if you want to calculate the wavelength in the Lyman series, so you just replace from the general Rydberg equation with the m, 1, and the integer number for n may start from the number 2, 3, 4 until infinity. And the last one, in the Paschen series, okay, we still use the same general of Rydberg equation to calculate the wavelength lambda here, but just replace the value of m with the 3, and the integer number for the n may start from the number 4, 5, 6 until infinity. Besides that, an element or an atom also can absorb the light at the specific wavelength. So the spectral line that correspond to the absorbed light will form as an absorption spectrum. So this spectrum can be obtained by passing a continuous radiation spectrum. So one containing all the wavelengths through a vapor of the element or atom being analyzed. So as the results, the absorption spectrum consists of a series of the dark line superimposed on the otherwise bright as a continuous spectrum. So each line in the absorption spectrum of a given atoms coincide with a line in the emission spectrum of the element. So as you can see from the given diagram here, so this is for the hydrogen atom example. So if the hydrogen is the absorbing vapor, so the dark lines here, okay, 1, 2, 3, 4, dark line here will appear at the 4 visible light colors at the different wavelength, okay, which is given here at the 656.3 nanometer at this point until the 0.41, 0.2 nanometer. So before I end my videos for to discuss, one simple example as given here, okay? So you can see the question is calculate the wavelengths of the first two lines in the Balmer series. So you have to give the two value of the wavelength in the first two lines in the Balmer series. So remember, recall back from my previous slide, in the way to calculate this wavelength, we may use the Rydberg equation, okay, as showing from this following equation. So I have a 1 over lambda, okay, wavelength here equals to RH multiplied by 1 over 2 square minus 1 over n square. So the value of RH, also known as the Rydberg constant, so this is the fixed or constant value having 1.097 times 10 to the power of 7 in the unit per meter. Okay, so the n integer number for the Balmer series should be start from the integer number 3 and also integer number 4. So according to these two numbers, 3 and 4, so meaning that we can have two different value of wavelengths, okay, by using this equation. So I just substitute the first n equals to 3, okay, use the same as shown here, Okay, I got my first lambda, okay, equals to 6.56 times 10 to the power of negative 7 meter. You may try later. Okay, and then my second wavelength, when I use n equals to 4, so I got my second wavelength is about 4.86 times 10 to the power of negative 7 meter. So this one also you can try later. So before I end my videos, I would like to say thank you for listening my videos. Hopefully everyone can understand it clearly, and I will end my slide with Assalamualaikum and goodbye.
Okay, so that will be the slides, and then right. So let me share the slides first. Okay, so this is atomic physics. Okay, the chapter 28. So before this is chapter 27. Please bear in mind, at the end of the at the when we close to the end of the semesters, the chapters is quite okay short. Okay, in terms of the subtopics here, we not taking all subtopics in the chapters, but we take every the significant subtopics to be discussed during our lecture and also during tutorial. Okay, based on our lesson plan, of course. But you should know that this should be we are not explaining everything in the chapters. Okay, so just follows the lesson plan for you to understand, okay, which part that you should concentrate of the subtopics. Okay, okay, so for the subtopics is this one, so 28.1 until the 28.2. Okay, and 28.3 and until point 5 will be discussed by other persons. All right. Okay, so this is the learning outcomes. Right, so this is the Thomson model. Okay, so what is the Thomson model all about? Okay, suggested a model of an atom as a volume of positive charge with the electrons embedded throughout the volume, much like a seeds in the watermelon. Okay, seeds like a watermelon. Sometimes, okay, this one will not be in the subjective questions. Maybe it will come out in the objective questions. Okay, for some sort like this, okay, you should know that the Thomson's model look like. Okay, maybe they will give the picture, the figures, and you should know which persons suggested the model. Okay, so this is a Thomson's model by J.J. Thomson. So it's like an electron embedded in a big positive charge like a watermelon. Okay, simple. Right, so in 1911, Ernest Rutherford performed a critical experiment showing that Thomson's model couldn't be correct. Okay, so it's actually try to get the best of from the Thomson's model. So in this experiment, a beam of the positively charged alpha particles was projected against a thin metal foil. Okay, a thin metal foil, which using the LED screens here. This is the thin metal foil. Most of the alpha particle passes through the foil as it were empty space. Empty space, but a few particles were scattered through large angles. Okay, and remember, when the alpha particle passes through the foil, if it were empty space, but a few particles were scattered through large angles. Okay, so some of the particles will scattered through. Okay, this is a scattered through. Okay, and of course some even traveling backwards. Ada yang traveling backwards. Okay, some ada yang go straight with if it's a one empty space. Ada yang scattered through a large angle. Okay, ada yang traveling backwards. Maksudnya ada yang macam seolah-olah reflected. Such large deflections were expected. Okay, in Thomson's model of positively charged particle will never come close to a large positive charge to cause any large deflections. Okay, so that's why, okay, Thomson's model is not correct. Okay, because uh, when you talk about large positive charge, cannot cause a large angles of deflections. Okay, Thomson's just suggested a model of like a embed electron in the big positive charge. But when Rutherford took that particles, okay, to be tested in the lab or in the experimental, so he can see some of the light will go through straight without any deflection. Some will deflect with a certain angle. Some will traveling backwards. So you can have a variety of observations there. Okay, when you use the same model of Thomson, yeah, because you want to test the Thomson's model. Okay, so he might introduce to you that Rutherford explained that this results by making the assumptions that the positive charge in an atom was concentrated in a region called nucleus. Okay, so basically this is nucleus. Okay, that was small relative to the size of the atom. Okay, he visualized the atom's electron as orbiting the nucleus, much as planets orbiting the sun. So dibayangkan, okay, try to imagine this one as a sun and this one is a planet. Okay, orbiting the sun. Okay, orbiting the sun. Yeah. An atom. So basic difficulties of Rutherford's planetary model. So even though he tried to explain in his own terms, so he tried to get the attention to his model, but he's also having some difficulties because what happens is an atom emits a certain discrete characteristic frequency from the EM wave. Okay, and then the electron undergoes a centripetal acceleration. As the electron radiates energy, the radius of its orbital steadily decreases as its frequency of revolution increases. It leads increasing frequency of emitted radiation and the collapse of a atom as the electron spirals into the nucleus. So, when electron move in the very high speed, okay, it also the orbit, okay, that he actually tried to introduce will not be as much orbit as this one. Okay, instead, okay, it leads to the emitted collapse of the atom, and the electron will spiral. Okay, electron will spiral due to what? Due to the uh, increase in the frequency as the electron move in a high speed, because we know electron will radiate the energy due to the speed of the electron, and of course it cannot stay in the orbit just like the planets orbiting the sun. As simple as that. No, because when electron move in a very high speed, the radius of its orbit steadily decreases. Orbit decrease. Okay, that is the difficulties in Rutherford's model. Okay, so this is the atomic spectra. Okay, so what is atomic spectra all about? Okay, when you have a different element, for example, a hydrogen, a mercury, and also a neon, okay, you can look at this is a visible range from 400 nanometers to 700 nanometers, at about 700 nanometers. So each element will have a different spectrum. Okay, when the emitted light is analyzed with the spectrometer, so this is one using the spectrometer when you want to see the spectrum of the light. from each element. So you can discrete the bright lines, each having a different wavelength or color. So such a series spectral light is called emission spectrum. This is emission spectrum. So when you have a light and you use a spectrometer, so you can see a different color and a visible range. So we eliminate everything just to look at this color. Okay, so this is what we call emission spectrum, okay, as shown in the figure. So the wavelength of each spectrum are characteristics of the element emitting the light. Okay, so every element will have a different emission spectrum. Okay, in this case, we have three elements. Definitely, you can see the hydrogen will have a violet color at this point. Okay, and blue color, whereas the green color and the red color. So there are different region, okay, of course, different values of nano wavelength, okay, will give you different color. So when you look at the mercury and also neon, so you can see a lot of colors, okay, actually appearing, okay, but in the different wavelength. So we can see the wavelength of each spectrum are characteristics of the element. So it depends on the elements. All right. In this case, they want to show that this figure shows the emission spectrum of hydrogens. So we specifically look at the hydrogen itself, uh, uh, introduced by the Balmer. Okay, the physicist named Balmer. So he introduced with his own name of Balmer series. Okay, what is Balmer series? Consists of but prominent lines that occur at a wavelength at a certain wavelength. Okay, meaning that each colors that we see from this point, okay, the emission spectrum, look at the emission spectrum. So this is the whole thing. But when you focus on these four colors, okay, from violet, uh, this one is violet, right? Okay, violet, okay, blue, green, and also red. Okay, from the region of 400 nanometers to 700 nanometers. So this is the visible range, and to be on the side, we want to see the emission spectrum of the hydrogen, which consists of four prominent lines. Okay, so in order to do that, we can calculate. Okay, we can calculate the wavelength. How to calculate? How can they get the 410, 434, 486, and 656? How can they get that value? So using the Rydberg equations. What is Rydberg equation? 1 over lambda is equivalent to RH, which is the Rydberg constant. You just took until this point, okay? This point, 1.097 times 10 power of 7, okay? Not negative, 10 power of 7 per meter times weight, 1 over 2. So the Balmer series start at, okay, 2 times 2 power of 2, okay, minus with 1 over, okay, the n will start at number 3, which is 1 point higher than 2. Okay, so it start at 2, and the n should be 3 until infinity. Until infinity. Okay, so the wavelength, we can calculate the wavelength of the Balmer series using the Rydberg equations. And of course, the Rydberg equations is given by here. Okay, 1 over m square minus 1 over n square, then m should be always be less than n. The number of m should be always less than n. Okay, it's actually started at the Lyman, okay, which m equals to 1, Balmer m equals to 2, Pascal m equals to 3, and this one n will start at 2, 3, and infinity. And this one n started at will start at 3, 4, infinity. And this one will start at 4, 5, and then in the end, infinity. Okay, so these are the three. Can you see the slide?
Yes.
Yes.
Thank you. Okay, so Rydberg equations in the Pascal series, m equals to 3, and so on. Okay, so this is the atomic spectra. An element, okay, can also absorb light at a specific wavelength. Okay, the spectral lines. I'm sorry, can you see the slide?
Yes, sir.
Which part? Atomic spectra?
Atomic spectra.
An element can also absorb that one, or in general Rydberg equations.
Absorb.
Okay. Okay, so an element can also absorb light at a specific wavelength. Okay, the spectral line corresponds to this process form an absorption spectrum. Okay, so what I want to highlight here is the examples, right? Calculate the wavelength of the first two lines in Balmer series. First two lines in Balmer series. Remember Balmer? Okay, the Balmer series is M equals to 2 and n will start at 3, 4, and so on until infinity. So the first two will be 3 and 4. So that's why n equals to 3 and n equals to 4. Okay, so that will be the end of this part. Okay, so I would like to all of you to watch some pre-recorded videos. I think, okay, it should be enough. All right. To continue,
Assalamualaikum and good day. My name is Miss Masfiza Mustafa. Now let's continue chapter 28.3, Bohr's model of the hydrogen atom. These are the learning outcome for this subtopic, where at the end of this session, students should be able to explain Bohr's postulates for a hydrogen atom, relate the energy level obtained from the Bohr model, and calculate the radius of the orbits in the Bohr model, calculate hydrogen energy level. 28.3 Bohr's model of the hydrogen atom. The description of the structure of atoms, especially that of hydrogen, proposed in 1913 by the Danish physicist Niels Bohr. The Bohr model of the atom was the first that incorporated quantum theory and was the predecessor of quantum mechanical models. There are four assumptions of the Bohr model. The first assumption is electron moves around the nucleus in a circular orbit. The Bohr model is a planetary model in which the negatively charged electrons orbit a small positively charged nucleus, similar to the planets orbiting the Sun, except that the orbits are not planar. The second assumption of Bohr model is about the angular momentum. The angular momentum of electron orbiting around the nucleus is quantized. Bohr further added that electrons move only in those orbits where angular momentum of an electron is an integral multiple of h over 2. De Broglie hypothesis successfully proves Bohr's second postulate, stating the quantization of angular momentum of the orbiting electron. Thus, based on the hypothesis, the quantized angular momentum in the orbit can be written in this form, where n is the number of orbitals. As for the third assumption, Electrons is allowed in allowed orbits do not radiate. Radiation is emitted when electron changes from one orbit to another with frequency given by relation delta E equals to HF. Electrons can change orbit by releasing energy or absorbing energy. Now let's look at the radius and velocity of electron in Bohr's model. In order for an electron to move in a circle of radius r at speed v, the electrostatic force must provide the required centripetal force. It means that the magnitude of electrostatic force is equals to the magnitude of the centripetal force. So from there we get the first equation. And since the electron moves in a circular motion, then the angular momentum for electron in orbit is equals to nh over 2 pi. And at the same time, the angular momentum is also equals to I omega. Substituting equation 3 into equation 2, we can find the velocity of the electron in an orbital, which is equals to nh over 2 pi mr. Taking equation 4 into equation 1 yields the equation for the radius of the orbital. Okay, so n is the number of orbital. If you want to find the radius for the second orbital, we can substitute n equals to 2 into this equation. Okay, the value in the bracket is a constant value. Okay, if you see here, the h is the Planck constant, which is 6.63 times 10 power of negative 34. M is the mass of the electron, K is the Coulomb constant, E is the magnitude of the electron. I will show this in the next slide. So substitute equation Rn, okay, the radius, into equation 4. We can find the velocity of the electron, which is actually equals to 2 pi ke square over nh. Alright, from these two equations, we can say that the radius of the orbital is directly proportional to the number of orbital, and the velocity of the electron is inversely proportional to the number of orbital. So if the electron is away from the nucleus, then the velocity of the electron will decrease. Okay, if you substitute the constant values into this equation, okay, we will get 5.29 times 10 power of negative 11 meter. So basically we can say that the radius of an orbital is equals to 5.29 times 10 power of negative 11 n square. Same goes for the velocity of an electron in an orbital. Okay, if we simplify this, we will get 2.18 times 10 power of 6. Then the velocity of an electron is equals to 2.18 times 10 power of 6 divided by n. The energy of electron in Bohr's model. Now, previously we know that the velocity of an electron is inversely proportional to the number of orbital. It means that if the electron is away from the nucleus, then the velocity of the electron will decrease. Okay, now we want to look at the energy of the electron. The energy of the electron in each orbital. Okay, the energy of electron is the sum of its kinetic energy and potential energy. After some algebraic manipulation and substituting known values of constant, we find that the energy of electron in an orbital is equals to negative 13.6 z square over n square, where z is atomic number, n is the number of orbital. So if we want to find the energy for the electron in second orbit, then we can set n to be 2. Okay, however, remember Bohr's model is focusing on hydrogen atom, then Z is equals to 1 because atomic number for hydrogen is 1. So from this equation, we can say that the energy is inversely proportional to the number of orbital, meaning that If the position of the electron is away from the nucleus, then the electron will have lower energy. So the general equation specifically for Bohr's model is energy E is equal to negative 13.6 over n square. The change in energy of electron in Bohr's model. Now remember, light can be radiated from hydrogen atom if electron made a transition from one orbit to another orbit, right? So if in previous slide we know that each orbital has their own energy, depends on the orbital itself, given by equation negative 13.6 over n square, specifically for hydrogen atom or Bohr's model. So when the electron jumps from one orbital to another orbital, energy can be released or absorbed. Okay, so to calculate the change in energy, we can use this equation delta E equals to E final minus E initial. So by substituting the previous equation in previous slide, we can rewrite the equation in this form. Okay, so delta E is the change in energy equals to negative 13.6 1 over n final square minus 1 over n initial square. So basically it is actually delta E equals to negative 13.6 n final square minus negative 13.6 n initial square. Okay, you might also find a different formula, slightly different, but actually it is the same. Okay, some of the book may write this equation like this: 13.6 over n initial square minus 13.6 over n final square. So note that this equation is actually equivalent to this equation. Okay, they are all the same. It's just that you rearrange the value. Okay, so we know that if the change in energy is positive, it means that the electron absorb energy during the transition, and if the change in energy is negative, then it means that the electron emit energy during the transition. 28.6 atomic radiation. Okay, these are the learning outcome for this subtopic, where you should be able to define X-ray and state X-ray properties and application. Now, X-rays are a form of electromagnetic radiation similar to visible light. However, X-rays have higher energy and can pass through most objects. Okay, so medical X-rays are used to generate images of tissues and structures inside the body. The wavelength of X-rays are shorter than UV rays and typically longer than those of gamma rays. X-rays are produced when high-velocity electrons collide with the metal plates, thereby giving the energy as the X-rays and themselves absorbed by the metal plates. The X-ray beams travels through the air and comes in contact with the body tissues and produce an image on a metal plate. Soft tissue like organs and skin cannot absorb the high energy rays and the beam passes through them. So the dense materials inside our bodies like bones absorb the radiation. So white areas show the denser tissues such as bones, which have absorbed the X-rays, whereas black areas on X-ray represent areas where the X-rays have passed through soft tissues. Properties of X-ray. The X-ray's properties are given below. They have shorter wavelength of the electromagnetic spectrum. They requires high voltage to produce X-rays. They used to capture the human skeleton defects. They travel in straight line and do not carry any electric charge. They are capable of traveling in vacuum. Since the discovery of X-ray radiation, they are used in various fields. Okay, this is the example of the application of X-rays in medical science, security, astronomy, industry, and restoration. Okay, that's all for chapter 28. So basically under chapter 28, we learn about the early models of the atom. Okay, and then in 28.2, about the atomic spectra. Okay, where there are a few series named under atomic spectra. In 28.3, we learn about the assumptions of Bohr's model. Okay, there are 4 assumptions. And then we look at the radius, speed, and the energy of the electron in an orbital, and some qualitative part in 28.6, which is about the atomic radiation, focusing on the X-ray.
Okay, so that's all for today. Hope that everyone, I will explain the rest of the chapters, the rest of that pre-recorded videos during our class next week, inshallah. Okay, so